Well, I just want to go over a few of the key points that we've talked about in the previous simulations here, or the key modeling elements that we've gone over. The first, we had low-frequency fields are essentially screened from the interior of cells, and high-frequency fields penetrate cells, modulating organelle potential differences. So far we've been conducting simulations using the AC conduction module and electrostatics conduction module. Now, we found that the external fields are amplified across the cell membranes, and also we looked at the dielectrophoresis force that occurs in non-uniform fields, and it's either attractive or repulsive depending on the relative permittivity of dielectric particles relative to the environment. And in the case of the AC dielectrophoresis force, also depends on the conductivity of the particles and the background and so forth. So we've been doing these problems in axial symmetry as well as XY symmetry. So you can see additional examples in the two textbooks here for both biological applications and other applications in applied electromagnetics using QuickField and MATLAB, and also introductory biophysics perspectives on the living state. Both these are published by Jones and Bart Learning. So you can see jbllearning.com. And I wanted to talk about some of the other possibilities. For example, we looked at electrostatic simulations here and the field distribution of ion and dipole sources. So I've just sort of made a table here of different types of biophysical simulations that are possible with QuickField. Many of these are discussed in the textbook here, including magnetostatics, magnetotactic bacteria, forces and torques acting on bioelectric sources. And as far as AC magnetics, we can look at AC currents that are induced in cells and tissue by an alternating magnetic field, Joule heating, as well as transient magnetics with different types of excitations, field pulses, periodic waveforms, triangle waves, and delta spike type of waves, and so forth. Now we can also look at DC conduction. We've been looking at AC conductions in this webinar, but we can also look at DC conduction. And you can examine the bioelectric return currents due to action potentials, DC currents through gap junctions, and plasma organelle membranes, and so forth. Also, we can look at the heat transfer between biomaterials due to radiation, convection, conduction, and also modeling the heat generation due to metabolism. Also, we can do coupled field problems where multiphysics applications. For example, looking at the stress analysis, these biological membranes and external fields will experience electrical stresses, and we can model that with specifying the Young's modulus and Poisson ratio of bioelectric membranes. Also looking at stresses in different types of biomaterials such as bone. Now, for bioimpedance calculations, we can construct, QuickField has a circuit module where we can construct passive circuit models and model things like dendrite, passive signal propagation, gap junction models, and AC currents in tissues and so forth. And so stay tuned for future webinars where we discuss these different types of applications of QuickField to biophysical simulations. So that's all I have today, and I'll turn it back over to Vladimir, and we can answer any questions that you might have.
Okay, thank you, James. It was really interesting because as most of our audience today, I am an electrical engineer and was always eager to know what our customers from biology use with QuickField. Now I mostly understand. At level I could understand. So we got some questions from our audience. I sent the list of questions to James, and I hope he will answer some of them, which are easy to answer online. The rest will be answered by email. James, have you got the list?
Yes, I've got the list here. And it looks like that we have a question on the use of the biophysical simulations in teaching. And this, I use this QuickField in teaching a senior seminar and as well as a biophysics class. And what we have is I'll do simulations in QuickField, and we have a laboratory set up where we have using QuickField in the laboratory as well. It looks like there's another question on the use of QuickField, the experimental aspects of using QuickField. And I think that the best experimental application would be in designing different types of electrical probes, or depending on what application that you might have. So if you specify a different type of electrode configuration and you have a given sample cell you want to design for a given application, QuickField can be very useful for designing different types of sample cells depending on your given application.